Hi friends, welcome to our YouTube channel, Bright Education Center. In this video, we'll discuss about the chapter Mechanical Properties of Fluids. It's actually the part of mechanical properties of bulk matter. In the last video, we discussed about solids. Now here are the fluids we are going to discuss. I hope you've gone through the video solids. Now here in the fluids, what are the changes will be there when you apply the forces or when fluid moves through a container or fluid is at rest. So what are the significant terms related to these properties of a fluids that we are going to discuss in this topic. Here mainly two ideas you should know. What is density and pressure of a fluid? So fluid means anything which can flow. That means both liquid and gas comes under this category, fluids. Density and pressure. These two ideas we should have first. A primitive idea. In the lower sessions also you studied about it. So density is nothing but ratio of mass by volume. The amount of matter contained in a body in the available space or the space occupied, we could say about it. So in the given space, how much matter is included, contained. That's called the density term. It has the unit kilogram per meter cube. ml power minus 3 can be the dimension of density. Density of different objects are different. Some are more dense, some are less dense. Different mediums have different densities. So water, glass, air, these have different densities we have. So density is a significant term. Now if you compare the density of a material or a substance with respect to density of water, we will call as the term relative density. It have no unit because it's a ratio of density of substance to density of water at 4 degrees Celsius. You know the importance of 4 degrees Celsius for the density of water. Water has the highest density at 4 degrees Celsius. Above 4 and below 4, the density will be less. That's a peculiar nature of water. In the topic of thermal properties of materials, we'll come across it. Water is volume increases more than 0 degrees Celsius, and if it is cooled or hotter, in both cases volume increases, and volume will be the least at 4 degrees Celsius, not like another liquid or solids. So at 4 degrees Celsius, the water have the least volume and the highest density. So we mention it at 4 degrees Celsius. And the term pressure. Pressure, you know, force by area, the mechanical pressure concept. So in liquid also or gases, it has pressure. So any point below the surface of liquid, what will be the pressure exerted there by the fluid above that one? On the surface of sea, air is there about it. What is the pressure exerted by the air there? Because air has its own weight. That weight of the air exerts the pressure on the surface of sea water. We call as atmospheric pressure, P0. And different cases on different materials, the pressure will be different. So in liquid also, what will be the pressure? Hydrostatic pressure we call it as is given by P is equal to P0 plus H rho G. From the surface at a depth H, what will be the pressure? We can calculate P0 plus H rho G, where P0 is the atmospheric pressure at the surface and H rho G is the pressure exerted by the liquid column at the depth H. Rho is the density of the liquid, G is the acceleration due to gravity. The difference between P and P0, P minus P0 will called as gauge pressure. The difference between hydrostatic pressure and atmospheric pressure. P minus P0 will be equal to H rho G, that's called gauge pressure. So in order to calculate the total pressure below the surface of water, we have to add atmospheric pressure plus this H rho G. Then that's all the fluid statics. So fluid at rest, we'll get these all concepts. Now, if fluids moving through a pipe, then a term most important, equation of continuity. Equation of continuity is given by area of cross section of a pipe. Suppose it is not non-uniform pipe it is. So different areas have different parts have different area of cross section. So speed of water flowing through it also will be different. The liquid have different flow. Then A1 V1 will be equal to A2 into V2. So for the fluid, equation of continuity is given by the product of cross-sectional area and speed will be always constant. So If cross-section area is less, narrow, then speed will be faster, higher. Faster the liquid will flow or the fluid will flow through it. That is the product this constant is giving the idea. So this has the practical application, while gardening and all. If you press the mouth of the hose or pipe, you want to use it, the water flows faster. So speed increases there. In a broader pipe, if you take the narrower pipe, connected it, and the water speed will be faster through that. Equation of continuity can be used there. Fine. Then another one term, most important, is called surface tension regarding the fluid statics also. Surface tension of liquids or gases. The free surface of a liquid is always have an extra force there on the surface. This force per length is known as surface tension. The free surface of liquid, the molecules on the surface will get an extra force in downward. So it acts as a stretched membrane. This extra force per length is termed as surface tension. S is equal to F by L. Because of this surface tension, we have liquid drops, bubbles, etc. And we have capillary rise. So these are many aspects are there for this surface tension. The work done in forming a liquid drop is given by W is equal to 4 pi r square S. The drop have one surface, outer material, so 4 pi r square S. The surface area into surface tension will give you the work done. And if it is a bubble have two surface, two layers will be there, and a thin layer of liquid will be there. So work done in forming a soap bubble, W is equal to 8 pi r square into S. So you should multiply with the 2 here. So drop have a single surface and bubble have two surfaces. W is equal to 8 pi r square into S. Suppose a bubble is given, you want to increase its radius from R1 to R2, or a drop is given in the question, you can expect like that, then you want to increase the radius. For that the work done in increasing radius is equal to, for a bubble it is 8 pi S into R2 square minus R1 square. So the difference in work done. If it is for a drop, 4 pi S into R2 square minus R1 square. In increasing the radius of the bubble and drop, like this way we can do it. So surface tension by using the work done is required to increase the bubble's radius because of this extra force on the surface. Now suppose there are small drops are there many, you combine to form a bigger drop. Suppose there are n number of small drops are there of radius small r, you combine to form a bigger drop of capillary radius r, then the new radius of the bigger drop is given by n power 1 by 3 into r. The cube root of n you have to use it into small radius r. Then the work done in breaking that liquid drop, bigger one, will be equal to 4 pi r square S into n per 1 by 3 minus 1. So simple one to this one, to break the drops. So this is the radius of the new drop, and while breaking this will be the case. Now because of this surface tension, there is an excess pressure inside the bubble and drop. That excess pressure is given by, inside the drop, P is equal to 2S by R, where S is the surface tension. So excess pressure is because, a drop, to formation of the drop, external pressure given by the air or water in contact it is, and inside it is. So that excess pressure is, drop is given by 2S by R. And since there is two surfaces for a bubble, then for a soap bubble, the excess pressure P is equal to 4 into S by R. So you should multiply with the 2. 2 into 2S is given 4S by R, where R is the radius of the bubble. If this bubble is at the bottom, below the surface of liquid, inside the liquid level, then air bubble have the pressure P is equal to 2S by R only. And the total pressure there, inside the air bubble. So this air bubble, only one excess pressure is there, 2S by R inside. And if air bubble is there inside the liquid, then only one surface will be inside it. I hope you are getting the point. In a free surface, if air bubble is there, it have two surfaces because outside also air, inside also air. Now if this bubble is inside the surface of a liquid, under the surface of a liquid, then outside is liquid layer is there and inside only air is trapped. So only one layer is there, so 2S by R. The total pressure inside that bubble will be equal to P0 plus H rho g plus 2s by r. You have to add up this pressure also. So while any questions comes, please keep in mind that logic also. The total pressure inside a bubble below the surface of liquid level, P0 plus H rho g plus 2s by r. So excess pressure also because of surface tension also will be there. Fine. One of another concept, another idea because of this surface tension is capillarity. You know what is capillarity? A capillarity or capillary tube is actually a very narrow, thin tube of very small radius. In some millimeters range radius, that tube is called capillary tube. If this capillary tube is dipped in any liquid, the level of the liquid inside the tube will be higher or lower than the outside, because there will be an extra pressure or extra work, the height increase will be there inside the tube. That's because of surface tension. That rise in or fall of the capillary tube is given by H is equal to 2s cos theta by r rho g. This S is the surface tension and this theta is the angle of contact. So what is the angle of contact is actually, suppose this is a capillary tube. I'm done in magnified size. Suppose this is the liquid level at the surface. Meniscus will be there in a liquid because of this surface tension, extra force. And this meniscus, if you draw a tangent here, then this angle is theta. Angle between the solid inside the liquid surface and the tangent to the surface. This theta is called the angle of contact. It will be acute for this here in this case. It can be obtuse also in some other cases. Like mercury and all, it is obtuse. 2s cos theta by r rho g, where theta is the angle of contact, s is the surface tension, r is the radius of the tube, capillary tube, rho is the density of the liquid where it is kept, and g is the acceleration due to gravity. This gives you the rise or fall in a capillary tube. H is equal to 2s cos theta by r rho g. That theta content is very important there, angle of contact. So sometimes the drop can wet a surface. If it is angle of contact is obtuse. If it is acute, it won't wet the surface. Next, a term viscosity is another significant term in this chapter. Viscosity means actually when the liquid is in the motion, that is hydrodynamics, in the flow, between the layers of liquid, there is a frictional force experienced. This friction force reduces or dissipates its energy in other way. So the ability or the property by which that frictional force is arising is called viscosity. Sir Isaac Newton have given this viscous force on which all terms it depends. F is equal to negative eta a dv by dr. dv by dr is velocity gradient, that is velocity by distance. A is the area of cross section and eta is the coefficient of viscosity, is a property of the liquid. Different liquids have different coefficients, say constant value, and negative shows it actually a decreasing and opposing force. So Newton's force F is equal to negative eta a dv by dt, dr, velocity gradient. This eta plays a role in many cases. Like if a body is falling through the liquid, it will experience the viscous force. Then this viscous force F is given by Stokes law. We will get Stokes law. F is equal to 6 pi eta Rv. R is the radius of the pipe, V is the speed of the body moves. As the speed increases, the force, the viscous force, or this is also called a drag force, also increases. This eta is the coefficient of viscosity. 6 pi eta Rv gives this law. Now, the amount of fluid which comes through a pipe, or the rate of flow, volume per time, Q is given by pi into P r power 4 by 8 eta L, where L is the length of the tube, P is the difference in the pressure between two ends of the pipe. Then through the tube, this will be the amount of, there also this eta, viscosity plays a role. With the help of viscosity, again you can get the terms of terminal velocity also. The terminal velocity term gives an idea that when a body, a spherical ball, any object which falls through a fluid, like a parachutist, he jumped through the air. A spherical ball falling through the water. The velocity at which the net upward force acting on it is equal to its weight. So whenever net force becomes zero, upward force equal to downward force on this falling object, then the velocity is called terminal velocity. There will be a constant velocity because net force will become zero there. At that, terminal velocity can be given by 2r square. R is the radius of the body. Rho minus sigma into g by 9 eta. It has a viscosity, and this is the density of the fluid and density of the substance. Terminal velocity also we can get from this concept. Eta concept, you have to use it. So higher the viscosity, lesser will be the terminal velocity. There are also relations there if all other terms are kept constant. Now one more idea, what type of flows are there? The liquid can or the fluid can flow in two ways mainly, a streamline flow and turbulent flow. If velocity of each particle or the points of the fluid at a particular cross section is same or constant throughout this one, then we'll call it as the streamline flow or laminar flow. And if this velocity is different or in different directions are there, then the flow will call it as turbulent flow. To identify this streamline or turbulent flow, we make use of a constant called Reynolds number. This NR is given by rho d Vc by eta. This eta is a coefficient of viscosity again. And rho is the density of the fluid, d is the diameter of the pipe or the container through which it is flowing, and Vc is the critical velocity. Critical velocity is the velocity at which streamline flow changes to turbulent flow. If this value of NR is less than 2000, the flow will be streamline flow. And if it is between 2000 and 3000, it will be unsteady. That means it changes from streamline to turbulent. The changing phase will be there. And if it is more than 3000, NR is more than 3000, the flow is turbulent flow. So the flow of liquid can be either streamline or turbulent. That can be identified by using the concept of Reynolds number. So this all comes with the effect of viscosity, the concept. Okay, so that relative layers in their motion, they feel a frictional force. That property is called viscosity, and it depends upon area of cross section also and the velocity gradient, speed by distance. I hope you got it. Now regarding this flow, the energy of the flow, that's given by Bernoulli's theorem. In a flow there will be three energies. One energy is due to pressure, another is potential and kinetic. Bernoulli says that in the streamline flow, incompressible fluid, or we call it as an ideal fluid. Streamline, incompressible and non-viscous fluid. The sum of these three energy will be always constant. So pressure plus rho gh plus half rho v square. This gives you the kinetic energy, this gives you the potential energy, and this gives the pressure energy. Will be always a constant. So by using this concept, many applications are there. Application level question is to come. For example, in a railway platform, it's dangerous to stand near the way. When the speed train is coming, it can cause an accident if you're near the platform wicket. So you should move backward. It is because the moving train fetches the air with it. So that air will have higher speed. Kinetic energy will be maximum. If kinetic energy is maximum, pressure will be less there. Because some should be a constant. As the pressure in front of you decreases, your backside air may push you towards the train. So with the train you will stick together and you can do. It may cause an accident. A simple example of Bernoulli's principle. Like there many examples are there. So they're all, you have to take care that some of these three will be a constant. So one energy increases, and if one is constant, then the third one will decrease. Based on this, we can find this Bernoulli's principle. We can find the velocity of efflux. So overhead tank, water head tank and all, through an orifice, the outlet, how the water is coming out. Its speed depends upon the height of the orifice, the outlet, from the base to top, and the total height of the water also, and whether the tank is open to air or is closed. A general equation we have V is equal to root of 2g into h minus small h. This capital H is the total height of the water, level of the water, and small h is the height of the orifice, I mean the outlet from the base. 2 into P2 minus P1 by rho. P2 minus P1 is the pressure difference from the top layer and the outlet. If it is negligible, the pressure is open to air, tank is open to air, then P2 minus P1 will be equal, then root 2gh will be the equation for V. It's just like the free fall, final velocity of a body under free fall. V is equal to root 2gh. So water efflux, if open to air, tank is open to air, then V is equal to root 2gh. The equation we can have. And the time taken by the liquid to strike the surface, T is equal to root of 2 into h minus h by g. And the range, how far it will go, is given by V into T. So velocity into the time taken. If it is open to air, root 2gh into the time taken, you can multiply, you will get this value. These all equations will help you to solve the numericals from this chapter. So I hope you got these concepts clearly. So main topics are surface tension, viscosity, and flow of liquids from these ideas. Okay, so how to calculate the pressure we gone through it, how to calculate the work done, how to calculate the excess pressure we done it, and capillaries we done it, viscosity we done it, and terminal velocity, then drag force, viscous force or drag force, how to calculate we done it, and the energy consideration. These are the main topics of this top chapter. Please go through it. We can do some numericals. A question like this: the pressure on a swimmer 20 meters below the surface of water at sea level is the question. So here H is given 20 meters we have. You know the equation, below surface of liquid, P is equal to P0 plus H rho G, where P0 is the atmospheric pressure, that is 1.01 into 10 raised to 5 Pascal. One atmospheric pressure will call us. And H is the height is given, rho is the density, rho is equal to 10 raised to 3 kilogram per meter cube, mass per volume, and G you can take it as 10 meter per second square. So if you substitute here, you will get the total pressure P. If you just multiply it and rearrange, you will get almost is equal to 3 atm. The answer is D, is the option. You got it? It's a simple question. So how to use this equation? Here P0 is the atmospheric pressure, that's constant everywhere, and H, rho is the density of water, 10 raised to 3 you can use it, and G is the level. I hope you got this concept. But another question is like this way: a piece of solid weighs 120 gram in air, 80 gram in water, and 60 gram in liquid. The relative density of the solid and that of the liquid are respectively. That is the question. So it's given here is mass of the piece of solid is given 120 gram in air, and in water, so this is in air. In water it is 80 gram, and in another liquid it is 60 gram. So here you have to find the relative density. The expression for relative density you can write this way also: weight of solid in air divided by the apparent weight. Apparent weight means weight in air minus weight in liquid. So So we'll get the relative density of the solid. So if you put in this one, then what is the relative density? This equation also you can use it. So this will be, in air it is 120 divided by, apparent weight will be, in water it is 80, so 120 minus 80. That is nothing but 120 by 40, that is 3. So relative density of the substance is 3. Now relative density of the liquid is also asking. So that is in air minus weight in liquid divided by weight in air minus weight in water. That is 120 minus 60 divided by 120 minus 80. That is equal to 60 by 40, that is 3 by 2. So we got the equation for relative density of substance is 3 and for liquid it is 3 by 2. So the options D is correct of the solid and that of the liquid are respectively 3, 3 by 2. Now one another question is like this way. 8 equal drops of water are falling through air with a steady velocity of 10 centimeter per second. If the drops combine to form a single drop big in size, then the terminal velocity of this big drop is. So the terminal velocity equation, you know, Vt is equal to 2r cube into rho minus sigma into g divided by 9 eta. So that is r square. Vt is proportional to r square, you know, square of the radius of the drop, we can say. Now here 8 small drops combine to form a bigger drop. Then we know that the radius of the bigger drop r is equal to n power 1 by 3 into r. That gives you r is equal to, here 8 drops are there, so n is 8 power 1 by 3 into r. Cube root of 8 is 2, so r is 2r. So you got the radius of the total, bigger one is 2r and terminal velocity is proportional to r square. So here you have to find the terminal velocity of the bigger drop, you have to find out. So this comparison method you can use it. V is proportional to capital R square and that is V dash I am putting. V is proportional to small r square. Or V dash by V is equal to R by small r whole square. If you just take the ratio, that is nothing but V dash is equal to V into R, capital R is 2R, so 2R whole square by R square. Can cancel it, it will become 4 into V. So V dash is equal to 4 into V. And it's given initial speed is 10 centimeter per second. So 4 into 10, that is 40 centimeter per second. Here the concept what we used is combination of drops and terminal velocity. So terminal velocity is directly proportional to square of the radius. 2r square rho minus sigma into g by 9 eta. And the combined, when you combine it, the bigger radius of the bigger drop is cube root of n into r. So here n is 8, cube root is 2r. Then we got this one. Okay, fine. We can check on another question. Question is like this way. Pure water rises through a height h in capillary tube of internal radius r. If T is the surface tension of water, then the pressure difference between the water level in the container and the lowest point of the concave meniscus is. So this question is regarding the capillary rise and the surface tension. You know the capillary rise H is equal to 2s cos theta by r rho g. And the pressure difference P minus P0 is equal to H rho G. These two equations we have. Here S is the surface tension and the question is given T actually. So if you just rearrange this equation, this 1 and 2, if you rearrange it, you will get this as H rho G is equal to 2T cos theta by R. So this is the pressure difference P minus P0. Rho G take this side, so 2s cos theta by r will be. This theta is the angle of contact. So it is water, for water theta is equal to 0 degree. just wait about it. So angle of contact is 0 degree, we could say. Then cos 0 degree is 1. Therefore, H rho G is equal to 2T by R. So pressure difference will be 2T by R. The option C is correct. So here we used the concept of capillary rise and the pressure difference concept. I hope you got this concept. So the detailed worksheets will be provided in the session. I hope you watched it clearly. Make your notes and be thorough with this topic. Thank you for watching the video.
Bright Education Center, Medical and Engineering Entrance Coaching Center, Hilal area, Doha, Qatar. For further enquiries, contact 306000679.